All right, now in this video, we're going to look at the same two functions that we looked at in a previous video, but now we're going to find the area outside the circle, but inside this cardioid. And that some of the information that we need to obtain is going to be very similar, but the problem that we have to set up is going to be a little bit different. So let's consider also, again, we solved in the previous video for the angles that we had to work with. So we set the two equations equal to each other. 2 cosine theta. And in this case, the 2's are going to cancel. And then we're left with 0 is equal to 2 cosine theta. And the 2 obviously goes away. And then we're left with cosine theta equals 0. And therefore, theta is going to be pi over 2 and negative pi over 2. And again, we can see that from the graph. That's where the curves intersect with each other. Now, when we draw on the graph and we mark our area, our angles, we want to make sure, that didn't work very well. We want to make sure that the region that we're looking to find the area for is fully bounded by the angles. So if we look at the region that we want to find the area for, that's all this section out here. It is in fact bounded by these two angles. There are some times where we draw the angles and we find out, oh, there's a little bit of section that is left outside the region that still satisfies the conditions of the problem, but isn't actually contained inside of the curve that we're looking for. And so you do need to keep that in mind as you're setting these up. It's not just that the intersections always are going to be the limits of integration. Sometimes they will be, sometimes they won't be. It's going to depend a little bit on the curves that you're working with. If you flip the orientation of the curves around, you might get slightly different kinds of results where sometimes they will be bounded entirely by these two curves on the outside, or you may find that there's some small section where you still have to consider a region that is still outside, for instance, the inner curve, but is still bounded by the outer curve, but now it's not accounted for inside those limits of integration. So it's always important to draw these curves, to be very careful about how you set them up, and make sure that, in fact, the region that you want is actually fully contained inside the angles that we're working with. Now, we are going to use symmetry to make our life, when we plug in values, a little bit easier. We're just going to do this top half and then multiply by 2. Now, this is a area between two curves, and so we do also need to take that into account. The outer curve is the cardioid. The inner curve is the circle. So let's set up our area equation. We're going to double it because we're using symmetry. And then we have 1/2 integral. We're going to go from 0 to pi over 2 to do the top half of the region. The outer curve is the cardioid, and then we square it, and then we subtract off the area of the inner curve, also squared. Now, it's important to kind of keep this in mind. You do need to square the outer curve and square the inner curve separately. Some people are tempted to just subtract them and then just square what's left. You can't actually do that. Essentially, keep in mind what we're doing here is, if we look back at our drawing, what we're essentially doing is we're going to find the area of the entire cardioid between these two angles. That's the whole area. And then we're going to subtract off the area inside the circle. And that means that you have to essentially do these as two, it has to be equivalent to doing this as two separate integrals. So calculating the area on the inside the entire cardioid between the intersections, and then subtracting off the area of the circle. That means you square the cardioid and then you subtract off the square of the circle. So they have to be squared separately. All right, so once we have this, then we can go ahead and we can do our squaring, cancel the 1/2. Zero to pi over 2. Squaring everything out, we get 4 plus 8 cosine theta plus 4 cosine squared theta minus 4. And so our 4s are going to cancel, which is nice. So that 4 is gone, and that 4 is gone. But then I still have to replace my power reducing identity to get rid of cosine squared. And so this will get replaced with 1/2, 1 plus cosine of 2 theta. And 4.5 will give me 2. And then if I distribute that, I'll get 2 plus 2 cosine 2 theta. And if I integrate, I end up with 8 sine theta plus 2 theta plus sine 2 theta evaluated between 0 and pi over 2. Now, if I plug in pi over 2 into sine theta, I'm going to get 8, because sine of pi over 2 is 1. And then if I plug in 0, I'm going to get 0. And then 2 theta, if I plug pi over 2 into that, I'm going to get pi. And then pi over 2 into sine 2 theta is going to give me sine of pi, which is 0. Plugging in 0 is also going to give me 0. And so I'm left with 8 plus pi.